Something is sitting in a SpaceX facility right now that hasn't existed in over 50 years. Not a blueprint, not a simulation, not a render posted to social media to generate press coverage. A real, physical structure, steel, welded, standing, designed to carry human beings from lunar orbit down to the surface of the moon. The last time humanity had something like this, Neil Armstrong was 38 years old. SpaceX has just revealed major progress on the Starship human landing system, the vehicle NASA has selected to return astronauts to the moon as part of the Artemis program. And the details they've released aren't just technically impressive. They reveal a vehicle so fundamentally different from anything that came before it that calling it a lunar lander almost undersells what it actually is. This is the story of how humanity is going back to the moon, and why the machine being built to take us there is unlike anything our civilization has ever constructed. Let's start with what SpaceX has actually confirmed. The primary structure of the Starship human landing system is complete. This isn't a mock-up arranged for press photos or a CAD render released to satisfy investors. The physical skeleton of the vehicle, its hull, its framework, its bones, has been manufactured. Engineers are now preparing to install the life support systems, the power systems, and the avionics that will transform it from a steel shell into a spacecraft capable of keeping human beings alive. That distinction matters more than it might seem. In aerospace, building the primary structure is one of the most complex and risk-laden phases of any vehicle's development. It's where engineering theory collides with physical reality. Tolerances that look perfect on a screen either hold or they don't. Welds either pass inspection or they don't. Material behavior under cryogenic temperatures either matches the models or it exposes every assumption the team made wrong. SpaceX has cleared that hurdle. What comes next? Integrating life support, avionics, and power is the work of converting a manufactured structure into a machine that can sustain human life in one of the most hostile environments our species has ever attempted to enter. But the first milestone, the one that separates ambition from hardware, has been reached. And in a program as technically demanding as Artemis, that distinction is everything. Before Starship HLS ever descends toward the lunar surface, it faces a challenge that most coverage of this mission barely mentions. It needs an almost incomprehensible amount of fuel. Starship is, by far, the largest spacecraft ever designed to land on another world. Propelling a vehicle of this mass from Earth orbit to the moon, and then conducting a controlled powered descent to the surface, requires propellant quantities that no single Starship launch can carry in full. So SpaceX and NASA have engineered an orbital refueling architecture. The plan works like this. Starship HLS launches to low Earth orbit, but without a complete propellant load. A series of dedicated tanker Starships then launch separately, rendezvous with the lander in orbit, and transfer cryogenic liquid methane and liquid oxygen across the vehicles. Once the tanks are full, completing one of the most technically ambitious in-space operations ever attempted, Starship HLS fires its engines and departs for the moon. It enters lunar orbit and waits. NASA's Orion spacecraft, carrying the astronauts on a separate trajectory from Earth, arrives and maneuvers alongside. The crew performs a transfer, floating from Orion's docking port through the void of cislunar space and into Starship HLS. And then the real mission begins. The moment astronauts cross the threshold into Starship HLS, they enter a spacecraft that bears almost no resemblance to anything NASA has ever operated. The interior habitat offers roughly 20 times more living space than the Orion capsule they just left behind. Let that number land for a moment. 20 times. Orion is purpose-built for the journey to lunar orbit, efficient, compact, and remarkable in its own right. But it is not spacious. Starship HLS operates in an entirely different category of crewed spacecraft. The common areas are designed for genuine livability during the days crews spend in transit and above the lunar surface. Heated meals, Not food pouches squeezed in a cramped module, but prepared food in a functional galley. Touchscreen control interfaces throughout the cabin allow crew members to manage vehicle systems intuitively. Private sleeping quarters give each astronaut dedicated space to rest before and after the most physically demanding days of their careers. Exercise equipment is integrated into the design. For missions potentially lasting a full week on or near the lunar surface, physical conditioning is not a luxury. It is a mission requirement. Muscle atrophy and bone density loss begin quickly in reduced gravity environments, and a crew that arrives at the surface already depleted is a safety liability. But perhaps the most mission-critical system inside the vehicle is one the crew will hopefully never have to consciously think about. Starship HLS features an advanced closed-loop life support system. Unlike simpler open-loop systems that linearly deplete stored air and water consumables, a closed-loop system continuously recycles and reprocesses both within the vehicle. This dramatically reduces the supply mass that must be launched from Earth and substantially extends how long crews can safely operate. Week-long surface missions, a duration essentially out of reach for earlier lunar architecture concepts, are built into the baseline design. Here is a problem that required one of the most inventive engineering solutions in the entire Starship HLS architecture. Starship's Raptor engines are extraordinarily powerful. That power is precisely what makes lifting a vehicle of this size off Earth possible. But those same engines, fired anywhere near the lunar surface, would blast the regolith, the fine, ancient dust blanketing the moon, into a hypersonic spray capable of damaging nearby hardware, blinding sensors, and creating serious hazards for any equipment already positioned on the surface. This is not a theoretical concern. NASA's Artemis strategy involves pre-positioning scientific instruments, resource extraction hardware, and potentially early habitat infrastructure before crewed missions arrive. A landing event that sandblasts all of that with high-velocity regolith is incompatible with building a sustainable human presence on the moon. SpaceX's solution is structural. Starship HLS conducts its final descent and touchdown using a dedicated set of smaller thrusters mounted high on the vehicle, far above the surface. These thrusters deliver precisely the control authority needed to manage descent rate and achieve a stable landing, while the main Raptor engines remain completely off. The result is an approach that interacts far more gently with the regolith and protects equipment across the surrounding area. This wasn't a small adjustment to flight software. It required designing an entirely separate propulsion subsystem built specifically for surface proximity operations, a dedicated solution to a problem that simply didn't exist at the scale of any previous lunar lander. After touchdown comes what may be the single most visually striking feature of the entire vehicle. Starship HLS stands very tall. When the lander settles onto the lunar surface, the crew access points sit approximately 35 meters above the ground. That is roughly the height of a 10-story building. This is not a compact lander with a short folding ladder. It is a skyscraper touching down on the moon. In the Apollo era, astronauts descended to the surface via a ladder attached to one of the lunar module's legs. The relatively modest scale of that vehicle made that approach viable. At the scale of Starship HLS, a ladder is not just impractical, it is unsafe and wholly inadequate for transporting the volume of equipment that serious lunar science demands. SpaceX's answer is an integrated elevator system. When a crew member prepares for a surface excursion, they suit up and enter one of two dedicated airlocks built into the vehicle. The dual-airlock design is significant. It means the main pressurized habitat does not need to be depressurized each time a crew member exits or re-enters, preserving cabin atmosphere, reducing consumable loss, and simplifying logistics across multi-day excursion schedules. Once inside the airlock and sealed from the main cabin, the chamber evacuates. The elevator then lowers the astronaut, along with tools, sample containers, instruments, or any other equipment, down the full 35 meters to the lunar surface below. The return trip works in reverse. Crew members and collected samples ascend by elevator to the airlock. Repressurization occurs, and the habitat remains sealed throughout. The implications extend well beyond crew access. Equipment that could never have been safely hand-carried down a ladder, large geological instruments, portable science stations, potentially even small surface vehicles, can now be transported to and from the surface with precision. For the first time, the distance between a crewed spacecraft and the moon beneath it is not an obstacle. It is managed infrastructure. Every generation has had its version of this moment. The moment when a machine exists, physically exists, not as a proposal or a program name or a congressional line item, that could change where human beings are capable of going. In the early 1960s, it was the Saturn V taking shape in Michoud Assembly Facility. In July 1969, it was the lunar module descending toward Tranquility Base with 2 men aboard. In each case, there was a specific point, before the launch, before the landing, when a physical object sitting in a building represented the entire scope of human ambition, compressed into metal and wire and propellant. That object exists again. The primary structure of Starship HLS is built. Life support integration is coming. Avionics are coming. The mission, the first crewed landing on the moon since Eugene Cernan lifted off from the Taurus-Littrow Valley in December 1972, is no longer a line in a government strategic document. It is becoming a physical machine. What separates this moment from every lunar return promise made over the past 50 years is the sheer accumulation of capability assembled into a single vehicle. Week-long surface missions, 20 times the living space of Orion, dual airlocks protecting the habitat atmosphere across multiple excursion days, precision landings that safeguard surrounding infrastructure, an elevator system that fundamentally reimagines how humans and equipment reach the surface of another world. This is not the 1960s revisited. It is a reconstruction of what lunar exploration means, conducted at a scale, a duration, and a level of crew capability that reflects half a century of accumulated engineering knowledge compressed into one vehicle. The moon has not changed since Cernan left. The ship going back has. If this is the kind of deep-dive science and space content you want more of, the real engineering, the real stakes, and the real story behind humanity's next chapter beyond Earth, subscribe to this channel. Every week, we go further than the headlines. Drop a comment below. Which part of Starship HLS surprised you most? The elevator system, the closed-loop life support, or the orbital refueling architecture? Tell me which one you want broken down in more detail. I read every comment, and if you want to understand exactly how the full Artemis mission sequence unfolds, from launch day all the way to the lunar surface, that video is already waiting for you. It's right there, up next.